Cosmology is a field of profound inquiry into the origins, structure, and evolution of the universe. One of the most puzzling observations in cosmology concerns the cosmic microwave background, CMB, which is the afterglow of the Big Bang. Surprisingly, the CMB shows slight variations in temperature across different hemispheres of the sky. This contradicts the expected uniformity of the early universe, suggesting that something fundamental is missing from our current understanding. Adding to this mystery is the discrepancy in the value of the Hubble constant, a measure of how fast the universe is expanding, depending on whether it is calculated from the CMB or from observations of nearby celestial objects. These anomalies challenge the standard model of cosmology, which assumes a smooth and uniform beginning to the universe's expansion. Enter loop quantum cosmology, LQC, a theoretical framework that emerges from loop quantum gravity, LQG. Unlike classical cosmological models, LQC posits that gravity itself is quantized, composed of discrete particles or quanta. These quanta weave together the fabric of spacetime, imposing a minimum size, known as the Planck scale, approximately /10⁻³ -35 meters. According to LQC, this minimum size prevents the universe from collapsing into an infinitely dense singularity at the Big Bang. Instead, the universe may have originated from a G-bounce, where a previous contracting phase rebounded, initiating the current expanding phase. The concept of a bounce in cosmology suggests that before our universe began expanding, it was contracting. As all matter and spacetime compressed into a dense state, conditions reached a critical point where rather than collapsing into a singularity, the universe rebounded outward, giving rise to the hot, dense state we observe in the early universe. This bounce scenario offers potential explanations for several cosmic anomalies. For instance, it could resolve the unexpected temperature variations in the CMB by proposing that they are not anomalies, but rather artifacts of the universe's cyclic nature. In this model, the universe undergoes phases of contraction and expansion, smoothing out earlier irregularities and creating the conditions for the observed CMB patterns. Moreover, LQC addresses the curvature of spacetime in the early universe. If the universe had a high curvature during its infancy, this would imprint distinct patterns in the angular power spectrum of the CMB. These patterns, which represent the distribution of temperature fluctuations across different scales in the sky, serve as a powerful tool for understanding the universe's geometry and evolution. The implications of LQC extend beyond cosmological anomalies. They challenge the notion of a singular beginning to the universe and suggest a cyclic nature, where our current universe could be just one phase in an eternal cosmic cycle. This idea finds echoes in ancient philosophical and religious traditions that envision the universe as undergoing repeated cycles of creation and destruction. However, the concept of a cyclic universe is not without challenges. Theoretical models must account for the buildup of entropy, a measure of disorder in the universe, which increases with each cycle. The second law of thermodynamics dictates that entropy always increases in a closed system, raising questions about how a cyclic universe can sustain itself indefinitely without a continuous increase in disorder. Despite these challenges, LQC offers a compelling alternative to traditional cosmological models. By incorporating quantum effects into the fabric of spacetime at its most fundamental level, LQC provides a fresh perspective on the universe's origins and evolution. Whether our universe indeed began with a bang or a bounce remains a topic of intense scientific debate and investigation, driving cosmologists to explore new frontiers in our understanding of the cosmos. Cosmology, the study of the universe's origin, structure, and evolution, confronts profound mysteries through observations like the cosmic microwave background, CMB. This relic radiation from the early universe shows subtle temperature variations across its hemispheres, challenging the expectation of uniformity at the universe's inception. Such anomalies hint at a deeper complexity in cosmic history than previously understood. Adding to the intrigue, measurements of the Hubble constant, the rate at which the universe expands, yield different values when derived from the CMB versus local celestial objects. This discrepancy suggests that our current cosmological framework may be incomplete, prompting researchers to explore alternative theories like loop quantum cosmology, LQC. LQC emerges from the broader framework of loop quantum gravity, LQG, where gravity is treated as quantized, composed of discrete units or quanta. Unlike classical cosmological models, LQC posits that there is a fundamental limit to spacetime's granularity, the Planck scale, 10⁻⁻35 meters. At this smallest scale, spacetime's fabric prevents the universe from collapsing into a singularity at the Big Bang. Instead, it suggests a phase where a previous contracting universe bounced outward, initiating the current expanding phase. The concept of a cosmic bounce challenges the conventional notion of a singular beginning, proposing instead a cyclic model where the universe undergoes phases of contraction and expansion indefinitely. This cyclic nature could potentially resolve anomalies in the CMB, such as temperature variations, by suggesting they are echoes of previous cosmic phases rather than inconsistencies in our observations. Moreover, LQC offers insights into the early universe's geometry and curvature. If the universe began with a high curvature, this would imprint distinctive patterns in the CMB's angular power spectrum, the distribution of temperature fluctuations across the sky at different scales. Understanding these patterns provides crucial clues about the universe's shape, size, and evolution from its earliest moments. Beyond its implications for cosmological anomalies, LQC invites philosophical and theological reflections on the nature of time and existence. The idea of a cyclic universe echoes ancient cosmological beliefs found in various cultures, where the universe undergoes repeated cycles of creation and destruction. This perspective challenges our linear understanding of time and suggests that our current universe could be just one phase in an eternal cosmic cycle. However, the cyclic model is not without challenges. Chief among them is the issue of entropy, the measure of disorder in a system, which tends to increase over time according to the second law of thermodynamics. In a cyclic universe, each contraction and subsequent expansion would increase entropy, posing questions about how the universe can sustain itself across infinite cycles without succumbing to a heat death or other forms of cosmic decay. Despite these challenges, LQC represents a compelling avenue for exploring the universe's fundamental nature. By integrating quantum effects into cosmology's fabric, LQC not only addresses current anomalies, but also offers a broader perspective on cosmic origins and the nature of reality itself. Whether our universe began with a bang, a bounce, or through some other mechanism remains an open question, driving ongoing research and inspiring new insights into the mysteries of the cosmos. Cosmology delves into the mysteries of the universe's origins and evolution, exploring anomalies in the cosmic microwave background that challenge our understanding. Differences in temperature across its hemispheres contradict expectations of uniformity at the universe's outset, while the Hubble constant varies by measurement method, hinting at missing fundamentals. Loop quantum cosmology proposes a solution, suggesting gravity as composed of quanta-forming spacetime's fabric. It posits a minimum space size, preventing a Big Bang singularity and allowing for a universe that rebounds cyclically. This model potentially resolves cosmic anomalies and questions of cosmic beginnings, contrasting with traditional Big Bang theory.